So in the earlier lecture, I talk about time-varying magnetic field. Now in this lecture, I will talk about space-varying magnetic field, and the magnetic field is slowly varying. So let us begin. With the space-varying magnetic field. Space-varying means it's a del dot p. You have to think in terms of this factor, and this tells us about the space-varying magnetic field. So if I express this del dot p or del v, if in terms of tensor, and it can be expressed as a tensor of second rank. So tensor of second rank, in that form, this del dot b, it can be expressed as curly bx over curly x, curly bx over curly y, and curly bx over curly z, curly by over curly y, curly vi over it is curly x and curly vy over curly y, and curly vy over curly z, and it is curly v z over curly x, curly vz over curly y, and curly vz over curly z. So I will express it in this form. Now it contains different terms. So if these three terms are dominating, or if I am considering in these three terms, then this del dot p and rest of the terms will be 0. Then one case will arise is that curly vx over curly x, curly vy over curly y, and curly vz over, then it is a case of divergence, right? And if we consider these two terms, curly vz over curly x and curly vz over curly y, so, and if I consider the magnetic field is along z direction, then these two terms represents the gradient of v, and here if I will take vx and the curly z, or the vy over curly z, if I take these two terms, then it will relate to curvature. Related to curvature. So that means we will divide this article into three parts. We will divide this article into three parts. So first is the divergence, and second is the gradient drift, and third one is curvature drift. So in the first case, if I consider this first case, divergence, then means for the divergence, such type of path will be followed. It is z-axis, and second is the field gradient or the gradient drift. So it is x-axis, it is y-axis, and say it is z-axis. Along z-axis magnetic field is applied, and if gradient is along x-axis and along y it is 0, then such type of path will be followed. So it is known as gradient drift. And third case is for the curvature. It's like this: current drift or curvature drift. So I will talk about this later. So it is curvature drift. So this article is split into three parts. So first of all, I will talk about divergence part. Then in the next, I will talk about gradient drift, and last one is the curvature drift. So let us start with it. So for this, I am considering these diagonal terms. These are the diagonal terms which I am considering. And if I express these convert these Cartesian coordinates into the corresponding, because this is relating to divergence, so del dot B. So if I will consider the divergence terms or the divergence, so del dot P, it can be written as curly bx over curly x. It contains three terms: curly by over curly y and curly vz over curly z. It contains these three terms. And so I consider these, and what I consider that these two terms are non-zero. If these two terms are non-zero, then magnetic field is symmetrical about z-axis. Magnetic field is symmetrical about z-axis in this manner, and it is slowly varying. And its strength increases as z increases or decreases. With the increase in this, its strength will increases, and its strength, these two terms are non-zero, and magnetic field strength is increases with increase in z. Now so if I am considering the z-axis case, then RL curly B over curly Z must be less than equal to B. This I have taken from the condition that del B over B is less than equal to 1, because here I am considering the increase only along this, and these two terms are non-zero, means these two terms are constant like. So for that I am considering this condition, and this makes this for this particular case in this form. So this condition must be fulfilled. Here, this condition must be fulfilled. It is B. Now, let us consider the cylindrical coordinates for divergence. I will use that. So if we are having cylindrical coordinates for certain field A, then it can be written as 1 by rho curly over curly rho, rho A rho, plus 1 by rho curly A phi y curly phi, plus curly A z over curly z. Here A can be expressed in terms of cylindrical coordinates, and R can be written as, where this is the radius. So if these two terms are dominating, then this can be ignored. Variation along this can be ignored. So this case we have considered for the given case, the case which we have taken. So for this del dot B, it can be written as 1 by R curly over curly R, R B R, plus curly B Z over curly Z B. So this case we have considered, and it is equal to 0. Now this gives us this condition gives us that 1 by R curly over curly R, R B R, it must be equal to minus curly V Z over curly Z. So this can be written as curly over curly R, R P R is equal to R curly B Z over curly Z. So not neglecting, but taking integral on both sides. So if I take integral, then RBR must be equal to minus R square by 2 curly VZ over curly Z. Here what we have did, we have taken the integral, and this R will cancel out with it. So it means that BR is nearly equal to minus R by 2 curly VZ over curly Z. So now consider BR is non-zero, and what this BR will do, it will exert force on charged particle moving in circular path and forces along z-axis. So this BR exerts force along the z-axis and forces along z-axis, so that means it is directed along z-axis. So it means mdvz, because force is along, so acceleration will be along z-axis. So mdvz by dt is equal to E by c vr, right? So for this we have as we have studied earlier that mx dot is equal to E by C, E by mc, as we have studied earlier in the earlier lectures, that x double dot can be E by mc y dot b. Similarly, y double dot we have taken by E by mc x dot b. So in the similar fashion, because this is radial part and velocity, these two are perpendicular, because here it is z axis and it is x or the y. So similar fashion I can express it in this form. So from here what I can do, it is E y c, and what is this Vr can be written as minus r by 2. So it is a Larmor radius, so r is equivalent to Larmor radius, so it can be written as RL curly v over curly z. So it is minus E by 2c curly v over curly z. It can be expressed in this form. And RL omega c, this is nothing but RL omega c. So if I use this, so it will become minus E over 2c RL square omega c curly v over curly z. So this is nothing but this is the value of mu, means the magnetic moment, curly v over curly z. As we know that this mu is equal to ERL square over 2c omega c, and right. So that's what we have used it here. So therefore m dvz over dt, it can be curly v over curly z. So multiplying both sides by vz, so it is vz m dvz by dt minus mu curly v over curly z and vz, and this can be written as curly v over curly z, and vz can be written as curly z over curly t. It will cancel out with it, and these two terms collectively can be written as dy dt 1 by 2 mvz square, and this is equal to minus curly v by curly t. So this is one equation, and another equation which we studied earlier, that dy dt 1 by 2 mv, this is equal to 0. This we have studied earlier, which implies that dy dt half mv this square plus dy dt of half m v z square, this is equal to 0, and the value of it will be from the above first equation minus is equal to 0, and dy dt of perpendicular component of kinetic energy, this is equal to curly v over curly t. So if I take integral of these two sides, so I can conclude that ek perpendicular is nearly equal to mu b, or I can write down as that mu is equal to ek perpendicular over b. So this is the final result which we are getting. It's the kinetic energy perpendicular component. So that means it is constant. It is constant. So thus what we are concluding, that magnetic moment of charged particle moving in a slowly varying field is an adiabatically invariant. So with this, the first part of this lecture will complete. Now in the next we will talk about gradient paths or the gradient drift, and then later on curvature drift.